This video accompanies our article on bi-invariant distance vectors for homogeneous spaces. We discuss applications, introduce the different types of distance vectors, and conclude with a comparison. Distance vectors define a nearest neighbor relation. In this demonstration, each arrowhead represents a point in the three-dimensional special Euclidean group SE2. One can think of such a point as a position of a mobile robot in the plane that consists of a xy location as well as an angular heading. Here, each of the stationary points is labeled with one of three colors. The moving point, circumscribed in red, is classified based on the nearest neighbor in the set of stationary points. In this example, we color code the stationary points based on their proximity to the point of evaluation x. The dashed lines connect x to the 8 nearest neighbors. The stationary points can be referred to as landmarks. The idea of inverse distance weighing to build interpolatory functions was originally conceived by Shepard for points in the linear Euclidean space. The concept of inverse distance weighing also applies to the distance vectors in our article. The example shows a smooth function that interpolates values defined at control points as a heat map on the surface of the sphere. By projecting the inverse distance weights to a solution of the barycentric equation, we obtain generalized barycentric coordinates. These coordinates satisfy the Lagrange property. That means resulting deformations interpolate the control points. The concatenation of barycentric coordinates from one space and the weighted average in another space defines a smooth transfer of a domain. In this example, the two-dimensional unit square is mapped to a surface patch in the special Euclidean group SE2. Because the control points are interpolated, the mapping can be designed precisely. Next, we discuss the different types of distance vectors: metric, Mahalanobis, leverage, garden, and harbor. Pennock and Arzini have already pointed out in 2012 that the Mahalanobis distance is bi-invariant. We have used leverages in the construction of bi-invariant generalized barycentric coordinates in an article earlier this year. The garden and harbor distance vectors are introduced in our most recent publication. The property bi-invariance means that the entries in the distance vector do not change when the points pi and x simultaneously are subject to a symmetry operation of the space. The example shows points in the Lie group SE2 that undergo symmetry transforms. On the left, the metric distance vector that is not bi-invariant is shown. The entries of the vector vary. On the right-hand side, the bi-invariant Mahalanobis distance vector with constant entries is shown. The metric distance vector is computed using a fixed scalar product in the tangent space of x. The ith entry in the distance vector depends only on x and the respective point pi. Therefore, the vector is referred to as a vector of absolute distances. The entries of the Mahalanobis distance vector are computed using a scalar product in the tangent space of x that depends on all input points, namely x as well as the landmarks. The scalar product is generally positive definite and only degenerates for pathological point configurations. When a single point is moved, all the entries in the distance vector may change slightly. Therefore, the vector is referred to as vector of relative distances. A diagonal entry of the influence matrix is called leverage. The square root of the leverages coincide with the Mahalanobis distance vector. The influence matrix defines the projection to the solution space of the barycentric equation and is therefore relevant for deformations. An entry in the garden distance vector is determined by the Mahalanobis form in the tangent space at the respective landmark pi. In case only the reference point x changes, the scalar products at the landmarks can be pre-computed. Then, the computation of the garden distance vector is as fast as the evaluation of metric distances. An entry of the Haber distance vector is the norm between the influence matrix at X and the influence matrix at the respective point Pi. These matrices are projections and therefore can be thought of as points in the Grassmannian manifold. Next, we illustrate differences between the types of distance vectors using examples. Here, the images show the classification result and confidence level defined by a collection of labeled points in the two-dimensional Euclidean space, the sphere, and the hyperbolic space. The classification method is nearest neighbor using Mahalanobis distance, metric distance, and garden distance. In case of the metric distance, the classification corresponds to the Voronoi partition. In this example, landmarks in SE2 are color-coded according to their relative proximity to the reference location X in the center. The dashed lines connect the point X with the 8 nearest neighbors in the set of landmarks. Metric distances are omitted because the Lie group SE2 does not permit the definition of a bi-invariant metric. These images show the deformation of a square patch on the sphere using 3 different distance vectors. Only one of the 6 control points is relocated. The deformation defined by the Mahalanobis distance is not as local as when using metric distances. The garden distances result in a local but stiff deformation that is not injective in this case. Here is the implementation of metric, leverage, and Haber distance vectors, inverse distance weighing, and generalized barycentric coordinates in Mathematica. The definition of the logarithm is specific to the Euclidean space, otherwise the implementation is general. The graphics and animations from this video were generated using our open source library for nonlinear geometry computations in Java. Our article is available online. In the future, we plan to investigate the use of bi-invariant distance vectors in motion planning algorithms. Thank you for watching.